Welcome to Focus Math Plus. Dear students, let's look into the next chapter, which is chapter 3, the world of numbers. So, in this session, we are going to learn the introduction to the number system and also look into the questions from exercise 3.1. So, let's get started. So, this is the introduction given in your textbook. The dawn of mathematics, the need of human to count. So this is a brief explanation of the introduction given in your textbook, Ganita Manjari. The birth of numbers. Long before humanity built cities, formulated laws, or studied the stars, there existed a fundamental practical necessity, the need to keep count. For them, the mathematics did not begin in the classroom with the equations on the board. It began in the dirt, on the bark of the trees, and on bones. So imagine that you're living thousands of years ago in a small agricultural settlement in the banks of the river Saraswati. You have a herd of cattle. Every morning they go out into the dense forest to graze, and in the evening they return. How do you ensure that a calf has not wandered off? So without words for numbers and written without the symbols, early humans solved this thorough a concept called one-to-one correspondence. So how do we work with this? So for every cow that left the settlement, the herder might place one pebble in the clay pot. And in the evening, when every cow that returned, one pebble is removed. So if the pot was empty at the end of the day, the herd was safe. If pebbles remained, cows were missing. So this is how they decided if there were all the cows that have returned back or not. So this simple act of matching one object to another was the birth of the natural numbers. Right, so we shall look into all of these in detail. So this is how they use the strategies to count the number of cattle they had and whatever. So they use all of these and which is called as one-to-one correspondence. And this is how the number system originate the need to count. So let's look into the introduction and also the classification of numbers. So it all starts with the complex numbers. The number system starts with the complex numbers, and under complex numbers we have real numbers and imaginary numbers. You shall be learning this in grade 11. So right now we'll deal with the real number system. So the real number system comprises of all of these. I shall be explaining these in detail shortly. So we have natural numbers, whole numbers, integers, and also rational numbers. And all of these, in addition with the irrational, they comprise of the real number system. So we have all of these numbers in the real number system. We are going to learn about the real number system in grade 9 and imaginary numbers in grade 11. So let's look into detail of all of these numbers. First, we have the natural numbers. So it starts from 1. The counting numbers used to count objects 1, 2, 3, 4, and it goes on until positive infinity. And we then have the whole numbers. So the whole numbers include 0 as well. As you could see, whole numbers is comprising of all the natural numbers. In addition to the natural numbers, it also has 0. So zero was invented. It's a recent discovery in the number system, and zero was invented recently, and it was introduced in the number system because if we have nothing to count, we also need to have a number to represent it, and that's zero. The next that comes in line are the integers because we need numbers to represent temperatures which are freezing cold, and also we have to mention the distances under the sea level. So all of these and the basements and the elevators, so all of these have to be named as negative values, and so then the negative numbers were introduced in the number system. So as you could observe carefully, you can see that we have all of the natural numbers 0, 1, 2, 3, 4, etc., and goes on until positive infinity. And we also have negative 1, negative 2, negative 3, and so on until negative infinity. It goes on, which means so we have the negative numbers as well. So integers comprise of all the whole numbers and the negative numbers as well. And the whole numbers comprise of all the natural numbers and 0 as well. You could see that each time something is being added to the number system. Okay, and a very important fact that these numbers do they represent decimals, the natural numbers, the whole numbers, integers? Do they represent decimal? The answer is no. So all of these numbers are not decimals. So they do not represent decimals. They include whole numbers, a whole full number. So no decimals included in all of these three categories. So where would the decimals go? The decimals will be classified as rational and irrational numbers based on their types. So we shall be learning into these detail about it. Like say for example, if you have a number like a decimal which terminates, a decimal which ends, like 0.25, 7.327. So all of these numbers are categorized as rational numbers. Numbers such as, say for example, 2.355, and you see the dots behind, which means that this number is not ending, it's a non-terminating, and the pattern is seen. So non-terminating and repeating numbers are also rational. So they come under the rational number category. Okay, so they come under the rational number category. And the numbers which are non-terminating and non-repeating, say for example, numbers like 2, 3, 7, 5, 9, 4, and so on. You see the dots behind. The dots represent that these numbers are non-terminating and we can't see any pattern here. So these are non-repeating numbers. So you just have to remember non and non. So non-terminating, which means non-ending, and non-repeating. Non-ending and non-repeating numbers are called as irrational numbers. Okay, we shall be looking into these two categories later in detail with many more examples. So let's move on with the first three types of numbers. Okay, so as you could see, natural numbers are a subset of whole numbers. A whole number is a subset of integers, and integers are a subset of rational numbers, and rational numbers and irrational numbers together they comprise of the real number system. Okay, now just recall what did we have under the natural number system? We had 1, 2, 3, 4, 5, and so on, correct? Okay, what else did we had under the whole numbers? We had all the natural numbers including 0. Right? So what else did we had in the integers? We had the whole numbers, the natural numbers. In addition to that, we also had the numbers on the number line, which is -1, -2, -3, -4, and so on. Right? As you move towards the left, the numbers decrease. As we have seen in the coordinate plane in the chapter 1, the number line. So we have all of these. So the values on the number line, they represent integers. And the rational numbers, it can be terminating decimals, 0.25, something which is repeating. So all these are rational numbers. And irrational numbers, non-terminating and non-repeating. Say, for example, 8.2673. No pattern, and non-terminating. Non-terminating, non-repeating, rational. Besides this, all the other types of numbers are rational numbers. Okay, so natural numbers are a part of whole numbers. Yes, of course they are. Whole numbers are a part of integers. Yes, of course they are. Integers are a part of rational numbers, and together with irrational numbers, they form the real number system. So to begin with the exercise, we all have to know about the numbers. We have to know the numbers. We have to know what natural numbers are. We have to know what whole numbers are, and we also have to know what integers are. Only then we can understand the lesson care. Let's start discussing the first question from exercise 3.1, which says a merchant in the post city of Lotel is exchanging bags of spices for copper ingots. He receives 15 ingots for every 2 bags of spices. If he brings 12 bags of spices to the market, how many copper ingots will he leave with? So, like earlier, they didn't used to trade with money. So they used to exchange goods. So whatever they have to just exchange. And for the 12 bags of spices, we just have to find out how many copper ingots is he going to receive. So let's help these merchant trade with the goods, whichever they have. So let's write down this information. Like for every 2 bags of spices, he receives 15 ingots. All right. So you are to figure out, suppose if we have 12 bags of spices, say 12 bags of spices, how many ingots will he get? It's a very easy problem. Let's write that as a ratio. It's written as a proportion. So let's write it 2 over 15 equals 12 over x. So you could see that there exists a common factor. When you multiply this number with 6, you get 12, isn't it? And hence, you also have to multiply 15 with 6 to get to the answer. So you all must be knowing what is 15 times 6. 6 times 5, 30, carry over 3, 6 times 1, 6 plus 3, 9. So that gives us 90. So 90 is the answer. So easily done. So it's very easy. Let me explain another way to calculate the number of ignis would he receive. So write down the same proportion. 2 over 15 and 12 over x. You could just simply cross multiply. 2 times x is 2x. Just multiply the extremes. 2 times x, 2x, and 15 times 12. So just multiply 15 with 12. So 15 times 12, just do that manually, quickly, and you get the answer as 180. Correct. And since because you have to find out the value of x, when you transpose 2 to the other side, now this is 2 times x. So if you are transferring 2 to the other side of the equal sign, it goes as division. So 180 divided by 2, that gives us 90. So 90 is the answer again in this way. So likewise you can see 2 times x is 180. So we have to know what is x. So 2 times 90 is 180. All right. So there's another way to prove this. Like you can just write down the unit way. Wherein you can say that the 2 bags of spices represents 15 ignots and 14 bags are going to represent 30, 6 bags 45, 8. It just keep adding 15, 8 each time. Add 15 here because add 2 here because that is what we've been said. 2 bags of spices for 15 ingots. So just keep adding 15 each time. So 8 bags for 8 bags of spices you would receive 60 ingots. And for 10 bags of spices you receive 75 ingots. And for 12 bags of spices you receive 90 ingots. So this is one of the strategy to find out the solution to this question. There's another. For that, we need to find out the scale factor. Based on the question, it's given that 2 bags of spices in exchange for 15 ignis. So 2 bags in exchange for 15 ingots. So if you find out the scale factor is 15 divided by 2, which is 7.5. Now you have to figure out like how many ingots would you get if you have 12 bags of spices. So just one another step, which is 12 because you have 12 bags of spices and 12 times 7.5, that gives you 90 again. So you shall be receiving 90 ingots in exchange for 2 bags of spices. So this is another way. So you could see that this first question is being worked out in 4 different strategies. You can use whichever is feasible for you. For every problem, there's just one solution, but there are many approaches. Now let's look into the second question of this exercise, which says, look at the sequence of numbers on one column of the Shango bone, which is 11, 13, 17, 19. So the first part of the question says, what do these numbers have in common? So let's figure out what's common on these numbers. So as you have 11, 13, 17, are you able to recognize any pattern? Just look at these numbers carefully and see if you're able to recognize any pattern. Just think about it. Where have you seen this number and what could you relate? So 11, 13, 17 and 19. As you could see that the factor pairs that make 11 are just 11 and 1. 11 times 1 is 11. I do not get or couldn't think of any factor pair that gives me 11. Just 11 times 1, which gives me 11. Like 2 times 5 gives me 10, but not 11. And the next number, 13, this could also be obtained from the factor pair 13 times 1, which is 13. And I could see that no other factor pair gives me 13 as well, because 2 times 6 is 12, 3 times 6 is 18, and so on. So this is not getting any factor pair which gives 13. So the next number 17, and the same happens here. 17 times 1 is 17, and no other factor pairs make 17. And the same with the last number as well in the sequence, which is 19, and 19 times 1 is 19. And I could see that no other numbers make 19, like 3 times 6 is 18, and 4 times 5 is 20, and no factor pair makes 19. So this is what I get. So these are the only two factors of the numbers given. So let's look into these factor pairs. Do we see anything in common? We see that all of these factor pairs, one is common, isn't it? And the numbers itself. So these numbers have factors as one and the number itself. So as we reflect back to the definition of prime numbers, we could see that a prime number is the one which has only two factors, one and the number itself. So hence, what would you call these numbers? These numbers are prime numbers, because they have just two factors, one and itself. Now just look at the number 12, and let's write down the factor pairs that gives us 12. 12 times 1 is 12, 2 times 6 is 12, 3 times 4 makes 12. And just could you think of any other factor pair that makes 12? No, right? So we have all of these numbers. You could see that we got all of these factors: 1, 2, 3, 4, 6 and 12. So the factors of 12 are 1, 2, 3, 4, 6, and the number itself, which is 12. Okay, and we can see that this number 12 has 6 factors, and hence this is not a prime number. This is a composite number. Whereas the numbers which were given in the sequence, it just had the number itself and 1 as its factor. So all of these numbers, what do they have in common? You have to mention that these are prime numbers because they are divisible by 1 and themselves. And another way to see if the number is prime, you can just divide the number. So if you divide, say for example, the number 19 by the number 3, you can see that 3 divides 19 5 times. 3 times 6 is 18, 6 times, and the remainder is 1. So you shouldn't be getting a remainder. If you have a remainder and this number doesn't divide, so 3 is not a factor of 19. Say, for example, if you have 20 and you divide 20 by 4, 4 divides 20 5 times. 5 times 4 is 20. And when we subtract, we get a 0. We see that the remainder is 0. So hence 4 is a factor of 20 and 5 is also a factor of 20. So likewise, so all these numbers are prime numbers. I hope that's clear. And we also have to answer the second part of this question, which says that list down the next three numbers in this pattern. So as you see that the pattern is all prime numbers, right? So we start from 11, 13, 17, 19. And when you think about 20, 20 is not a prime number because 20 has factor pairs as 4 times 5, 1 times 20. So 20 is not in the list of prime numbers. So when you think about 21, 1 times 21 is 21, and 3 times 7 is 21. So as we see that this number 21 could be obtained by from the factor pairs 1 times 21 and 3 times 7. So this number 21 has 4 factors. So this is not a prime number. This is a composite number. So the next number is 22. And we could see that 22 is got from the factor pair 1 times 22, and 2 times 11 is also 22. So hence this is also having 4 factors, so this is not a prime number. And so the next number is 23, and I don't see any such factor pair that makes 23, nothing else other than 23 times 1. So 23 is a prime number. 24, let's talk about 24. We get 24 by multiplying all of these factors. 24, 1 times 24, 2 times 12, 6 times 4, 8 times 3. So all of these are the factors of 24. So hence 24 is also not a prime number, neither 25 because 5 times 5 is 25, neither 26. So because 13 times 2 is 26. So and then neither 27 because 3 times 9 is 27, nor 28 because 4 times 7 is 28. So the next number is 29 because we don't have any such factor pair that makes 29. And of course 30 is a composite number because 3 times 10 is 30. And hence the next number is 31 because no such factor pair other than 1 and the number itself makes 31. So the next three numbers in the sequence are 23, 29, and 31. So you have to remember all of these prime numbers. So the next three numbers in the sequence after 19 are 23, 29, and 31 because all of these are prime numbers. Now let's discuss the third question of this exercise 3.1. The question says, we know that the natural numbers are closed under addition. The sum of any two natural numbers is always a natural number. Are they closed under subtraction? Provide a couple of examples to justify your answer. So we have to prove that the natural numbers are closed under addition but not under subtraction. So we have to prove. For that reason, first let's recall what are natural numbers. Natural numbers comprise of numbers starting from 1, 2, 3, 4, 5, 6, so on. Right? It goes until positive infinity. And does it comprise of decimals? Yes. No, it doesn't comprise of decimals. And does it contain zero? No, it does not have zero because zero is under the whole numbers. It's not under the natural numbers. So the natural numbers start from 1, 2, 3, and it goes on. So we have to prove that this is closed under subtraction. What does it mean by closed? Say, for example, if you have a number, a natural number, say, for example, 4, and another natural number, 6, if you're going to add, sum means addition. So if you're going to add both of these numbers, you're going to get 10. So 10 is again a natural number. So this is also natural, this is also natural, and this is also natural. So this is called the closure property, wherein we say that the sum is also closed under addition, right? So let's try for another set of numbers, say like 5 plus 7. 5 is natural, 7 is also natural, and the result, which is 12, this is also a natural number. Okay, now let's try for subtraction, because the statement says that we know that the natural numbers are closed under addition, but we need to prove for subtraction. So 6 take away 4 is 2. Okay, 6 is a natural number, 4 is a natural number, 2 is also a natural number. But the other way around, 4 take away 6, is it just 2? No, it is negative 2. So in this case, we can see that 4 is natural, 6 is also natural, but negative 2 is not a natural number. So could you quickly recall what number is this? Yes, you're right. This is a negative number and hence this is an integer. So which means that it is not true for subtraction. Are they closed under subtraction? So the response is no. So we have to provide with an example. You can see an example here. 5 take away 3 is 2. 5 and 3 are natural numbers. The difference is 2, which is also natural. But example 2, 3 and 5, if you take away 5 from 3, you get the response as negative 2. So the negative 2 is not a natural number. So in this case, it is not a natural number. So you can write the conclusion. Natural numbers are not closed under subtraction because subtraction of two natural number can give you a 0. Also, it can give you a negative number as well. So you can just prove with another example to show that, say for example, 6 is a natural number. If you subtract 6 from 6, you get a 0. But 0 is not natural, it is a whole number. So it's not always a natural number. The result can sometimes be an integer and a whole number as well. Let's discuss the last question of this exercise 3.1. It says, ancient Indians used the joints of their fingers to count, a practice still seen today. Each finger has three joints, as you could see, 1, 2, and 3. And the thumb is used to count them. So we are not just counting on the thumb, we are just using the thumb to count these fingers. How many can you count on one hand? How does this relate to the ancient base 12 counting system? So as you could see, there are four fingers on which we're going to count the joints: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now let's see how do we count on these fingers using the joints. So we have three joints on each finger, as you could see: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So the numbers of fingers are four that we are using to count, and thumb is excluded. So the total number of fingers four and three joints on each. So 4 times 3 gives us 12. So we can count up to 12 using one hand. So relation to the base 12 system, since counting reaches 12 on one hand, it naturally leads to a base 12 counting system used in the ancient times. So therefore, total count is 12. This explains the origin of the base 12 counting system. So this was the origin, like using the hand and the joints to count the numbers. Let's recap the number system. And we have the natural numbers starting with 1, 2, 3, and so on. And we then have the whole numbers. and then the integers, and then the rational. So as you could see, natural numbers is a subset of whole numbers, and whole numbers is a subset of integers. So I hope that was clear. And drop your answers in the comments for this question. All natural numbers are whole numbers, but not all whole numbers are natural numbers. Explain why. So with that, we come to the end of this exercise, and thanks for watching.